Okay, people, this is the second half of Unit 4. This dealt with what were called continuous and discrete random variables, and then the properties associated with them, and how to do things like expected value and standard deviation for a random variable. And later on, we get into Chapter 16, which was Bernoulli trials and geometric and binomial probability models. So, what I've done here, this is the study guide I sent to you. I have the answers already typed up on here. So what I'm going to do is walk you through it and highlight what the answers are. You can always take a moment to write the work down and pause as we go through. So to start with, in general, expected value is basically like the average. And what happens in these problems is there's usually an amount, a lot of times it's money, and there's a probability associated with that amount that might be different than the probability associated with a different amount. So expected value is almost like a weighted average. You basically multiply the probability times the amount plus the probability times the amount, and that is your final answer. So generically, that's what's right here. This is actually on the packet you got from me, the one with the information that they share with you on the day of the test, but now you can just use this if you like. And we talked about standard deviation being the square root of variance, and how you do that in a problem like this. You would basically have to find expected value first. You subtract the expected value from the amount, square it, and multiply it by the probability. And then you add, take away again the amount minus the expected value, that quantity squared times its probability, and then you take its square root. Now, this is just in general. If you see a problem that fits what's called a geometric or binomial model, there are specific formulas for their expected value and standard deviation that are different than this, but this is the nuts and bolts of what this concept means. All right, now, operations on these. I don't know that you'd see just a verbatim question like this on this year's test, but you might be asked about doing operations on, and you'll see that kind of in a context with question 3. But just so you remember, this is all outlined up here. But if you forgot or just want to see it in example form, we'll take a look. Basically, what they're saying here is that expected value of a random variable plus or minus a constant, you just add the constant onto the expected value or subtract it. If it's multiplied by a constant, same thing. And if you're adding or subtracting two random variables and their expected value, it's just the sum of their individual expected values. So everything with expected value is very straightforward. However, when you deal with standard deviation, it's a little different. The good news, you can really get away with just using standard deviation, except when you're adding two or more random variables or subtracting them. And so let's take a look at that here. So you were asked to multiply 0.8 by the random variable y. Well, the expected value of that, as you can see here, you just multiply the expected value by 0.8. And same with standard deviation. I know the formula above talks about variance, but you could just multiply it by the standard deviation. That's okay. Now, another thing is, what if you have both multiplying and then in this case adding or subtracting a constant? Well, expected value is everything is as is. So you find the expected value of 2x, which is 2 times the expected value of x, and you take away 100 from it. However, with standard deviation and variance, anytime you add or subtract a constant, you just ignore it. So really, this becomes the standard deviation of 2x, which becomes 2 times the standard deviation of x. Now, here's where things get different. When you have two random variables, x and y, and you are multiplying and subtracting, or in this case adding, things are a little different. So D is a little easier to explain than C. And again, you can see here, expected value, it's just adding their two individual expected values. Something to remember, when you have to add two random variables, here you can't just add their standard deviations. You have to treat it like Pythagorean theorem. So what I've done here is pointed that out to you. The standard deviation of the sum of two random variables is the square root of the sum of their variances. Now this is kind of going in reverse. We usually say standard deviation is the square root of variance, but that means that variance is standard deviation squared. And that's why this is sometimes called the Pythagorean theorem of statistics. where you'd have to square each standard deviation, add it, and then take the square root. Here, a little more challenging. You have expected value, again, not a problem. You're going to do 3 times the expected value of x minus the expected value of y. But with standard deviation, again, we have to, because it's 2 random variables, deal with the square root of their variances first. What happens when you do that? If you go back up here, if you are adding or subtracting with variance, sorry, it's right here, it always becomes addition. You don't transfer over subtraction, it just becomes addition. That's why this isn't a typo. I wrote this as plus. Second, when you pull a constant out in front of variance, it's actually squared. That's up in the formulas as well. And then you had to convert these to their standard deviations squared and then proceed as follows. So again, I don't foresee that necessarily being a straight up question, but you might be asked something in context, which is what question 3 is about. So these are the times for 4 swimmers, and it's a medley, and they each swim a different stroke. Here's their mean times and their standard deviation. So this is 4 random variables. And if you were asked to find their mean and standard deviation, well, again, the mean or expected value, you just add these. That's pretty easy. Notice for standard deviation, you can't just add them because they're multiple random variables. You have to square them and add them and then take their square root. So these 2 numbers represent expected value and standard deviation. Now this has a twist, and this is leading to what will be Unit 5. They're saying each swimmer follows a normal model, and they're independent, meaning you could use a z-score or a normal model if you are asked a follow-up question about the probability of something. So you'll notice up here, they didn't ask you what's the probability they get this contract, but they could have. And that's what's asked here. So if your information fits a normal model and is independent, if you're told that, or you can infer that, you could do this. So part B said the team's best time so far this year is 199.48 seconds, which is a little under their average. So with a standard deviation of 0.461, is this enough below average to suggest that they could do this like on the reg, or are they going to have a difficult time beating this personal best of their season? So I wrote out here what I just explained. We can use a normal model. Here's a z-score being put into action, and I get a z-score of negative 2.36. So whether you use a chart or whether you use a calculator, which again, if you need to figure out anything with a normal model, you would have gone to second VARS and picked normal CDF. You would have made this negative 99 because you're looking for anything at that z-score or below. This, if you remember, was negative 2.36. You leave 0 and 1. And what we're basically trying to figure out is what's the probability I land between these two. And it's very low. So that's where I got that answer of 0.009. You could have got that from a chart as well. This is the work you would show for that, even if you did use your calculator. And I would argue this is unlikely. They only have a 0.9% chance of swimming faster than their best time, given their mean and standard deviation. So chapter 16 takes those things we've learned and builds on them. So now we're looking at the beginnings of Unit 5 as well, because first of all, Bernoulli trials, that just means in the problem you're looking at, are there only 2 possible outcomes, success or failure? Is the probability constant for each, like do you know what the probability of success is going into it, and does it stay the same for each trial, and are the trials independent? So if those 3 unique criteria are met, you can use either a geometric model or a binomial model depending on the problem. Now, these other things here, the 10% rule, that's, again, previewing. If you can't tell if they're independent, if Bernoulli trial category 3 is kind of violated, if you're dealing with something that's less than 10% of the population, it's okay. You know, we've talked about that before. The success failure condition, that's something that comes up in Unit 5 as well, but they're kind of previewing it here, saying if you're doing a binomial problem, which we'll get into in just a second, If it's a significantly large amount of trials, like if n is big, well, you might be able to paraphrase and summarize with a normal model so long as you have at least 10 successes and 10 failures. And that's what units 5 and 6 go off of and kind of like build upon. But you start to see that in this unit, but we won't dwell on it too much. I just wanted to point that out to you. That'll be for a later video. And then statistical significance, that's hypothesis testing. That's determining if what you just observed is highly unusual. Without hypothesis testing, you basically learned that if it's 2 standard deviations above or below average, that's very unique. But again, we learned how to formally prove that in the later chapters. So what we're going to talk about right now is what's a geometric model, what's a binomial model. Again, they actually didn't write the standard deviation here. I don't know why. This is from the text, but they did here. So these are 2 unique situations where if you have a Bernoulli trial and you want to find expected value and standard deviation, you would use one of these 2. Now, geometric model is when I'm trying to count the number of trials until I get my first success, whereas binomial model is when you are counting the number of successes in a fixed number of trials. So let's see that in context. So let's say Cheerios is running a promotion. You want to get a LeBron James card, and there's a LeBron James card in 20% of Cheerios boxes. So first of all, this sounds like a Bernoulli trial because there are only 2 possible outcomes. Each time you open a box, you either did or did not get the LeBron card. Is the probability of success the same each time? Yeah, it's 20%. Are they independent? Now, technically, you could argue as you continue to open boxes, you potentially altered the percent because it's without replacement. You're not going to close the box up and put it back on the shelf. However, for our case here, you're only opening maybe 10 boxes or so. So you're going to be less than 10%. Or even if you opened a whole bunch of boxes at a grocery store, that's still less than 10% of all the Cheerios boxes in the world. So we can assume this independence via the 10% condition. Okay, so now, what's geometric probability model? This would be if you are asked any question about how long until my first success, how many trials until my first success. So expected value when you're dealing with a geometric model is this, 1 over p. So 1 over that probability means I should expect to have to open 5 boxes until I get my first LeBron card. Now, this was what was missing up above, and this one's actually given to you on, I don't think this one's given to you on your formula sheet either. So this will be your formula sheet. The standard deviation is Q, which is the probability of the complement of not getting LeBron, over p squared, and you take the square root of it. So 0.8 over 0.2 squared, take the square root. That's how you would find the expected value and standard deviation in a geometric model. Now we're going to put this to work. So this is just expected and standard deviation. All you do for a geometric problem is you either use your calculator or think like this. It says find the probability you find your first LeBron card in the 5th Cheerios box. That's like saying the first 4 you didn't find one. That's like saying fail, 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 success, which is like saying 0.8 to the 4th. That's the probability of not getting LeBron 4 times in a row. Same probability each time, and then times 0.2. If you're more comfortable, though, you could use second vars and geometric PDF. So again, second vars is where we find a lot of things in these later units. If you hit up, that's the quickest way to get to these. PDF is always for a specific, distinct amount. CDF, in both of these cases, is what's called cumulative. That's when it says something like at least or up to or at most in the context of the problem. So by picking PDF here, because it was specifically on the 5th box, I get the same answer. In the next one, it says what's the probability it was in one of the first 4 boxes. That's another way of saying it took at most 4 boxes or up to 4 boxes. Now the official work, you don't have to write all this. If you have the time when you take the test, they would like to see this. The probability of being less than or equal to 4 boxes is like saying I could have got it on the first box, the second box, the third box, or the 4th box. And again, this is the probability you got it on the first one. Boom, 0.2. Here, you failed and then succeeded. here you failed twice and then succeeded, and so on. Or since this is cumulative because you're adding a sequence, you could use geometric CDF. And what you see here with the 0.2 and 5 and the 0.2 and 4, that's like this. P, that's the probability of getting LeBron, that's 0.2. X is the number you're using, like how many trials until you got that card. Now, binomial, why this can be tricky, it's the same setup. It's a Bernoulli situation, but instead of asking how long until I got my first success, it's saying how many successes could occur in a set number of trials. So let's say you are guaranteed to open 10 boxes. What's the probability you find a LeBron card twice among those 10 boxes? So in this case, when you use binomial PDF or CDF, and again, I'd highly encourage the calculator here. The formula is really weird. What you would do is 10 is the number of trials, you'd say. 0.2 or P is the probability, and they'll call it X. That's the number of successes you are looking for. And because this was specifically twice or 2 cards, that's how you'd enter that in. What that looks like over here, if I go to second vars, it looks like, one second here. There you go. So you have the probability that you would enter in right here, and then the X value. Oh, I hit the wrong one. Sorry. Calculator's being a little slow. Okay, so if I can get up to here. All right, ready? Did it again. All right, I'll get back to that. I don't know why it's doing that. Let's try it one more time. Second, vars, and we'll pick capital A. I got a big delay here. I don't know why it's taking so long. There you go. Now you can see that there's 3 inputs: trials, probability, and then number of successes. Okay, now again, this is PDF because it was specifically 2 cards. These are both CDF. Find the probability of finding up to, that's like saying less than or equal to 4. So you wanted to find cumulative and 4 as the number of successes. And lastly, if it says at least 4, that's like saying 4 or more. So here's a case where we had to use a complement. I had to do 1 minus, because when you type in like this right here, when you type in binomial CDF like this, what the calculator understands is I'm doing 10 trials, I have a 0.2% or 0.2 is the probability of success up to 3. So that's like saying I got 1 or 2 or 3 successes. And I want to say the opposite of that. I want to say 4 and more. So that's why I would have to do 1 minus here. Now, something I didn't write here was an expected value and standard deviation problem. So you could have found the expected value, meaning how many successes should I expect in a given number of trials, and that's where you would have used this information right here. The expected value when you do a binomial is just n times p. So if I did 10 trials times 0.2, I would expect 2 successes. That's what that would represent. And the standard deviation would be the square root of n times p times q. All right, so that is it. Again, I'm going to stop here. If you were doing a significantly larger number of trials, like let's say n was 200, then that's a case where you probably wouldn't want to use binomial CDF and PDF. You could estimate any binomial situation with the normal model, so long as, and there's a big so long as here, so long as you have at least 10 successes and 10 failures. So if you had that, you could just use the normal model instead. And that's what you start to see with Unit 5. So the next video we do, Unit 5, that's where you first learned about confidence intervals, margin of error, and began to do hypothesis testing with proportions and 2 proportions or a difference of proportions. And then Unit 6, if you recall, the same setup but with sample means. So more videos will be forthcoming. Hopefully this helped. Any questions, let me know.